in a case which is relatively rigid compared to the propellant. The propellant itself, as seen here, is a particulate composite. Can you all hear me about this? You can't? Okay, is it better?
That's better.
Okay. So the propellant is a particulate composite composed of viscoelastically behaving propellant, the binder, and the particles are mainly the fuel that burn when the rocket is launched. The behavior is classified as viscoelastic, and also typically the propellant goes under large deformations, so we call it as nonlinear viscoelastic behavior. That sort of summarizes the briefly behavior. At the time of loading, we are interested in this particular application is that of a storage, meaning the propellant, the rocket stays in the storage for long periods of times. So the main loading is subjected to is temperature loading that goes up and down during the day as well as during the year. So we have a minimum and maximum limits of temperature the propellant undergoes typically. So in these structures, as far as fracture is concerned, two critical locations are that of the inner surface that we call bore cracking, and the interface between the propellant and the case, and this we call debonding. As outline of this exercise, first I'm going to look at a couple very simple benchmarking problems that we studied in order to explore some of the relatively newer techniques that can be used in nonlinear viscoelastic media in modeling cracks. And then I will look at the applications of these methods in first bore cracking and then debonding. All analyses were performed in finite element package abacus. The version I don't recall now, but it's in paper. As far as these methods are concerned, we are interested in first, of course, the conventional finite element based method. And as alternatives, we consider cohesive zone method and the extended finite element method, etc. In the conventional finite element based fracture mechanics, typically what we do, we assume a location and size of a crack. And the main importance of the finite element, the conventional method, is the fact that the mesh has to conform to the geometry of the crack, meaning the crack surfaces have to be overlapping the element edges or sides, and the crack tip has to coincide with the element node. So the conventional method is very much mesh dependent. Then what we do with the traditional method, we assume a certain crack growth criterion, and according to this criterion, we decide whether the crack decides to extend or no. If it extends, then we go to the next size of the crack, in which case we most likely need to remesh our model. So remeshing is almost always needed if we use the conventional finite element method. Also, in order to accurately model the singularity of the crack tip, we need to use local refinement. Both of these typically are, they increase the cost, the computational cost of the conventional finite element based fracture mechanics analysis. So alternatives that some of these have been used in different applications, but not much in rocket industry. The first one is the cohesive zone modeling, which allows the more accurate modeling of the physics of the problem, and it removes the singularity at the crack tip. Therefore, there is no need for local refinement. Typically, this is done by introducing, computationally, it's done by introducing cohesive elements. These elements have their own constitutive behavior that we describe as traction and separation. They work pretty simply computationally. The disadvantage that one might have is when the crack growth path is not known a priori, one needs to insert these elements all around the mesh. So again, the computational cost becomes high if the crack path is not known. A relatively new technique, which is based on finite element method, is the extended finite element method, which basically uses some enrichment functions in the interpolation of displacement, and it removes the need of the mesh to conform with the crack geometry. Therefore, the need for remeshing is minimized with this new technique. So it's very promising in that regard. However, it is still in the sort of development stage from computation point of view. So there are certain limitations. You cannot use all element types. It is not yet verified for all types of material behaviors. And parallel processing is not possible. However, these two techniques, the cohesive method and the extended finite element, depending on the application, are very promising for the type of problem I tried to summarize at the beginning. So in order to explore these techniques, we first looked at two very simple benchmarking problems. The first one is single edge crack subject to tensile loading. The media is linear elastic mainly because this is what the results of this problem were available in the literature only for linear elastic media. So our benchmarking is against what was published in the literature. And as a result of this analysis, what we did, we ran the analysis for using conventional finite element method, using extended finite element method with various options, and the cohesive zone method. And we looked at how the crack propagates in time, the history of the crack propagation, and we verified that all methods pretty much gave similar results. So this increased our confidence a little bit, so we went to the next benchmarking, which is a double edge crack, again under tensile loading. This time, the material is actually propellant. However, in the literature, the results in the literature were for linear viscoelastic material, so this is what we did as well. So we modeled it with the linear viscoelasticity available in Abacus, and again we benchmarked XFEM solution against the conventional finite element solution, as well as comparing the results against those published in the literature, which were based on cohesive zone method and some test data. And what we compared with was the reaction force, the history of the reaction force. And the results again were, as we see here, sort of not too different from each other, except some convergence difficulty that we had with XFEM towards the end of the analysis. And honestly, we did not explore this further, whether it was modeling issue or XFEM issue, but we proceeded with the application in the kind of more realistic problem. So the first type of problem, as I mentioned, is going to be potential cracks at the bore. So in modeling the cracks, again, as I said, we're interested both in stationary cracks and the effect of these cracks in the distribution of the stress, as well as propagating cracks. The interest in the first is results from the fact that there is some maturity in the industry as far as health monitoring sensors are concerned. These sensors claim to measure the temperature as well as the stresses at the interface between the grain and the case. And finite element analysis is very valuable in helping where to put these sensors as well as evaluating the results. So first part of the interest in crack modeling is to put several cracks at the bore. As we see here, for example, at a certain angle, and see the effect of this crack on the stress distribution along the bone line that is at the interface between the grain and the case, because this is where the sensors are placed. This is where they can detect any change in the stress distribution, and we are interested in finding in the finite element analysis whether they can do this or how they can do this better. And for example, one of the results is how the bond stress, the radial stress at the interface changes with the circumferential location. Okay? The details you can find in the paper, so I go relatively fast. This was done under cooling from a certain temperature down to room temperature. And it was also done for cyclic temperature loading that kind of mimics the storage loading we're interested in. Next is the modeling of the propagating crack. For bore cracks, namely the cracks at the inner surface, we don't know the crack growth path, so it's advantageous to use XFEM. These are simple models, of course, from computation point of view. There's no difference between using cohesive zone method versus extended finite limit method, but our interest is really to show that this can be done with one method or the other. So for a cooling from 60 degrees to minus 40 degrees, we looked at the propagation of the crack, the history of the basic crack propagation. And we did this for different initial crack sizes, starting from 2 millimeters to 32 millimeters. We obtained the counterplots of the bond stresses, and all was run successfully, at least from a convergence point of view. Next, we looked at the cracks which are located at the interface between the case and the grain, and this we call debonding. Again, we evaluated the effect of these debonds on the stress distribution. And then we looked at the propagation of these debonds. In this case, since the path, the crack growth path is known to be along the interface, we use directly cohesive zone elements. Here you see the example of the mesh. Again, the loading is either cooling or cyclic temperature loading. And for both of these cases, we obtained the counterplots of the bond stresses, as well as the propagation history of the cracks. And we deducted some conclusions, some very preliminary conclusions, main of which says that both of these techniques can be applied to nonlinear viscoelastic media, at least for the geometry we considered successfully. One of the more specific results for temperature cyclic loading, it seems that the cracks propagate only during the first cooling part, which sort of needs to be checked against test data. We didn't have any test data for majority of these. And perhaps one of the most important things to do in the future would be really to evaluate in detail the numerical robustness of these techniques for more complicated geometries, such as the actual motor, which is going to have lots of stress concentration areas, and for the initiation and growth of the cracks. So I'll stop here. If you have any questions, I'll be happy to